Alright, so what I want to look at with you today is just a couple of examples using these inverse trig functions. So the first thing that we're going to do, it's actually already worked out here, but I just want to walk through the analysis here. We have an inverse trig graph of arctangent of x squared. Okay, now notice it's not x squared, it's the arctangent that is being squared here. Okay, so so you'll remember here, if we're told to, it just says analyze the graph. So what we're going to do is we're going to look through and find max and min points. We're going to find points of inflection, look at increasing and decreasing, look at concavity, and figure all of that stuff out here, okay? So if you recall what we looked at yesterday, the derivative of arctan of u is u prime over 1 plus u squared, okay? U prime over 1 plus u squared. And in this case, we just have an x for our u, okay? So the derivative, the u prime part, is just going to be 1, all right? Now, notice here we did need to take the derivative using the chain rule because our outer function is something squared. So that's why we have 2 times the arctangent of x now to the first. That's the derivative of the outer function. And then we're multiplying that by the derivative of the inner function, the 1 over 1 plus x squared. Okay? Again, it's 1 because u equals x, so u prime is just a 1. Okay? So we simplify that a little bit and we have 2 arctangent of x over 1 plus x squared. So at this point what we have to think about here is, okay, what is our domain and range? Because that's gonna help us determine what the domain and range of this derivative is as well. Okay, so when we're talking about the arctangent, what was the domain?
Like every real number.
All real numbers. Okay, if you think about your tangent graphs, looked like this. Okay, it went off to infinity at the top and the bottom. So the domain was all real, the range of the tangent was all real numbers, so the domain of the arctangent was all real numbers. Okay? Now, the range here, you have to consider how we made tangent have an inverse function. We did that by, if you recall, we only included one period of that tangent graph, okay? And that was how we made it 1 to 1. So we went from negative pi over 2 to pi over 2, okay? So the range is, with parentheses, negative pi over 2 to pi over 2. I would say, well, why in the world are we talking about that? Well, the reason why we need to consider that is because if we're going to look at where our max or min points are, we're going to set this first derivative equal to 0. Okay? Remember, critical numbers occur when the function equals 0 or is undefined. Well, 1 plus x squared is never going to equal 0, not with a real number. So we now need to look at, okay, well, where does 2 arctangent of x equals 0? Well, that occurs when arctangent of x, I don't know why I keep using an n, arctangent of x equals 0. So if we take the tangent of both sides, okay, tangent of both sides, we have x equals tangent of 0. And what angle has a tangent of 0? 0, yeah, because tangent sine over cosine, and sine is 0 at 0. So that means we have 0, okay? That's our only critical number, all right? That's our only critical number, and if we were to then, let's say we did a sine diagram with the y prime to look at what's going on with y. If I plugged in, say, a -1, arctangent of -1 is going to be a negative pi over 4, because the tangent of negative pi over 4 is -1, okay? So that's going to be a negative pi over 4 times 2 divided by 1 plus x squared is always positive. So I know that's going to be negative, which means this is decreasing, okay? If I were to plug in a positive 1, arctangent of 1 is going to be pi over 4, so that's going to make y prime positive. So now you can see here by the first derivative test, this value corresponds to a relative minimum, okay? Also notice here, if I were talking about intervals of increasing and decreasing, it's not negative infinity up to 0. Keep in mind what the domain and range are, okay? Well, I'm sorry, no, the domain is all real numbers. So the interval of decreasing does go from negative infinity up to 0, and then it is increasing from 0 to positive infinity. Okay? And then we have that minimum point there at 0, whatever that is, okay? Arctangent of 0 is 0, squared is 0, so that actually is at the origin, okay? The relative minimum is at 0, 0. Okay? Now, the second derivative. That's talking about our increasing and decreasing. Now we're going to look at second derivative to determine concavity to finish our analysis. Okay, so second derivative using the inverse, or I'm sorry, the quotient rule. We have the derivative of the first of the numerator. So the derivative of 2 arctangent is going to be 2 times the 1 plus 1 over x squared. So it's 2 over 1 plus x squared times the denominator, 1 plus x squared, minus the numerator, 2 arctangent of x, times the derivative of the denominator. Okay, so you can see here we're using the quotient rule to find the derivative of 2 arctan x over 1 plus x squared. We do some simplifying, okay? Here the 1 plus x squared will cancel out. Okay, so we have 2. They factored out a common factor of 2 here. So we factored that out. And what's left is a 1 minus 2x arctangent of x over 1 plus x squared quantity squared. Okay? So now we need to think through, okay, well, where are we going to get our points of inflection? Okay, well, that's going to be where this thing equals 0. So that's going to be where 1 minus 2x not tangent, arctan of x equals 0. What's that?
Did I forget my computer started here?
So we won't go through all the work for that, but we've got x is approximately plus or minus 0.765. Those are going to give us our points of inflection, okay?
Is
And
that, oh, I'm sorry.
and that means that that we have what you see here, points of inflection. If you were to plug in a 0.765, you would get this point here, and negative 0.765 would get you the other one. So those are your 2 points of inflection. Here's that minimum we found earlier at 0, 0. And then the horizontal asymptote, okay, the horizontal asymptote goes back to, remember our range, okay? The range for arctangent is a negative pi over 2 to pi over 2, okay? I should have written arctangent because I wasn't really considering the whole function squared, okay?
Wait, why is our
But-
tangent negative pi over 2 to pi over 2? Oh, because it's negative at the, okay, I get you.
Yeah. So then if we take the limit, if we look at what's going on with those values, it's going to be approaching pi squared over 4. Arctangent squared is going to approach pi over 4 squared, okay? Or I'm sorry, pi squared over 4, which if you think about it, okay, think about the range of arctangent. If the range of arctangent was a negative pi over 2 to pi over 2, okay, if you square arctangent, then all these negative pi over 2's become a positive pi squared over 4. All these pi over 2's become a positive pi squared over 4. So that's how we're seeing that there is a horizontal asymptote at pi squared over 4. Okay? And then the 0, 0 being the minimum, that means the range of this function, the range of y, is 0 to a positive pi squared over 4, not including that value. And actually I should have parentheses, not brackets here. Okay. Because there are asymptotes there on the original arctan. Okay? So that's our first example, just kind of looking at these things. We can also then look at intervals of concavity. Okay? Concave up and concave down. It's concave up between that negative 0.765 to positive 0.765. Okay. Okay. It's concave down from negative infinity up to a negative 0.765. And from positive 0.765 to positive infinity. Okay? Alright.
Mr. Dixon.
Yeah.
This day 2, there's really nothing. There's nothing new in this lesson. It's just applying these new concepts to the very old problems like going to.
So let's look at a practical application of this whole process here. We have an image here illustrating a situation where we're taking a picture of something, and the camera that we're using is on a tripod that is X units away from the wall, okay, and it's 1 foot below the bottom edge of what we want to take the picture of, okay? So notice there, that's 1, and we're X units away from the wall itself, okay? Now, let's look at more of the facts of the problem, then we'll come back to this picture, okay? It says a photographer is taking a picture of a 4-foot painting hung in an art gallery. The camera lens is 1 foot below the lower edge of the painting. That's what we just saw. How far should the camera be from the painting to maximize the angle subtended by the camera lens? Okay, well that's subtended. What are we talking about?
That's a made up word.
It's not a made up word, but it's close. All right. That just means the angle that the lens will actually be able to see on the picture.
Oh.
Okay. So notice here there are two angles. There's the angle from the horizontal up to the bottom edge of the picture. Okay. And then there's the angle from the lens up to the top of the picture, okay? And from the horizontal up to there, okay? So notice that's alpha up to the bottom edge, and from horizontal up to the top edge is theta. So this B, or beta, is really what it is, the Greek letter beta. Okay? Hello. This Greek letter beta is what we're trying to maximize, okay? We want to find the maximum of beta, where beta is theta minus alpha, okay? So it's the angle between those two lines of sight, you could say. All right? In some applications, we would call this the apparent size. We measure this in radians, and we call it the apparent size. So let's think about how we would start coming up with some kind of a function. Because really, if you think about what we're trying to maximize, if we're trying to maximize beta, remember our optimization problems that we've done in the past, you need to write a function with beta of x, maybe?
Do we know alpha?
No.
So we need to find it too?
Well, maybe. Let's see what happens.
Well, if it's a constant, then we should. But I mean, okay. So the first thought that comes to mind is using the basic. It's not sign. It's tangent equation. So
Okay.
We're trying to find the angle using.
Bless you, oh my god.
Using its tangent.
You
So
okay?
the tangent of this. Yeah. So is it fine if we find the theta first?
Well, here's the thing. Let's think in terms of the parts that we're given here, and let's just start writing things down. Let's not necessarily try to find anything this moment.
I got it.
Let's just start writing down any kinds of equations or relationships that we can identify at this point. Okay.
May I try to assume what is gonna be? So I just found it out. So there is an alpha, and alpha is it an angle? It should be an angle.
Yeah, it's an angle.
Alpha is an angle, and beta is beta minus alpha. So the bigger the alpha is, the smaller our angle is, and we need to maximize our angle. So alpha needs to be at its smallest. So we find the and we now.
Well,
we look at
hang
that.
on. One thing you got to understand here is that theta is not going to be constant. If I move this closer, then theta is going to get bigger.
Of course. Yeah.
Okay, now alpha will get bigger, but so will beta, because theta is getting bigger. Okay, so you can't. Let's start writing down some relationships here and try to come up with, before we get too buried in theory, or trying to figure out the answer before we actually have anything. Let's start writing some things down and try to actually come up with a function, okay? So what's any relationship that you can see, some kind of an equation that you can see to write this down?
Theta equals arc tangent 5 over x.
Okay, theta is the arctangent of 5 over x. Okay, that'll work because, again, theta is going up there, so the opposite is the full 5 feet, the adjacent is x, so that'll work, okay?
Alpha,
Someone else, what's another equation that we could write here?
And you don't know the hypotenuse though, right?
What?
Can you find the hypotenuse? No, because you don't know what x is.
Yeah, we don't know what x is.
Okay. Could you do alpha equals opposite over adjacent? So it'd be arctan
Uh-huh.
of 1 over x.
Arctangent of 1 over x. Okay. So can anyone give me an equation for beta in terms of x?
arctangent 5 over x minus arctangent 1
No,
over x.
no, it would be 4 over.
What? What do you mean 4 over?
Why is it 5 over?
Because take a look at the model. It's 1 plus 4.
Okay. Notice I get what you're saying here, but if we use the 4, then we can't use the x because this is not a right triangle here.
And we don't know the hypotenuse yet.
And we don't know, yeah, we don't know that there.
Respect.
Okay. So, but yeah, this is why, guys, before we get too buried in theory or guessing or whatever, just a good problem solving strategy is just look at what you're given and start writing down any kind of relationship. Maybe you did say, okay, well, the hypotenuse of that would have been, you know, x squared plus 1 squared, square rooted. And that would have been, you know, the square root of x squared plus 1. Or maybe you did the big hypotenuse and you said, okay, well, then that would be 5. So it'd be x squared plus 25 square rooted.
The class is actually over.
Okay? Could we actually get to a solution using this method?
Maybe?
Sure.
Take forever.
What would we have to use here to find beta?
You have to use
It was
crap. I forgot what it's called. I know exactly what it is. It's like
How about law of cosines?
no, that's what it was. Yeah. Because like
Yeah.
when you know all 3 sides. but
Do
you
we
don't
want to
know
have to
the
screw
angles.
around with the law of cosines here? No. This function over here is a whole lot simpler, and then we can take the derivative of that, okay, find beta prime of x,
And then, don't see no class though.
and then solve it for when it equals 0. So let's actually find our solution. First of all, we've got to take the derivative here. Okay, so the derivative of arctangent of u is u prime over 1 plus u squared. So let's, with this first one here, u is 5, I'm going to write that as 5x to negative 1. U prime is going to be a negative 5x to negative 2. Okay, and u squared is going to be 25 over x squared. Okay, so, and this is negative 5 over x squared. So we actually here have negative 5 over x squared over a 1 plus 25 over x squared. Okay, and I'm going to simplify that here in a minute after I get my other part. Okay, have a similar one here with the arctangent of 1 over x. It's actually going to be the same except all the 5s are 1s. So that's going to be a negative 1 over x squared over a 1 plus 1 over x squared. Okay? And now I'm going to simplify. I'm actually going to simplify by multiplying, and the reason for doing this is just to make this easier to work with later on. I'm going to multiply this by x squared over x squared, and this by x squared over x squared. And that's going to end up giving me b prime equal to a negative 5 over x squared plus 25 minus negative 1, so it's actually be plus 1 over, and I'm going to have an x squared plus 1. Okay? Now I did that because that's going to make it a whole lot easier on our next portion, which is, in order to get the solution, I need to set this equal to 0 and solve it. So I'm going to make it negative 5 over x squared plus 25 plus 1 over x squared plus 1, and I'm going to get a common denominator here by multiplying this fraction by an x squared plus 25 over itself. And I'm going to multiply this by an x squared plus 1 over itself. So now I have a common denominator. I'll put all this together because I'm setting this equal to 0. So I have a negative 5x squared minus 5 plus x squared plus 25 over an x squared plus 25 times x squared plus 1. Simplify the numerator. And notice here, at this point I can disregard the denominator because it's never going to equal 0. So I'm just going to look at this negative 4x squared plus 20 that's in my numerator. Okay, and that's going to mean that x squared equals a positive 5. So x is plus or minus square root of 5. Okay? Now, because x in our image here has to be positive because it's a distance, that means x is positive square root of 5 feet. So that's where we should put the camera in order to maximize that angle beta. Now, we are assuming that this is the max point since it's the only critical point, but let's go ahead and confirm that just to be sure. So, I'm going to put radical 5 on our sign diagram. Let's check beta prime, see what that does to beta. If I plug in a 0, I have negative 1/5 plus 1. Okay, that's going to be positive. So this is looking promising. It's increasing as we approach radical 5. Square root of 5 is about 2.23. So if I plug in, say, a 3, or we could even, let's just do a 3. I'm going to have a negative 5 over 34. So negative 5 over 34 plus 1/10. So plus 1/10. That actually comes out to a negative 0.047 and so on. So that is what we were hoping it would be. It's negative, so that means we're decreasing. So that does confirm that we have a maximum when x is radical 5. Now, let's go ahead and make sure that we answer the question. It says, how far should the camera be from the painting to maximize the angle? So it doesn't actually ask what the angle is, but it asks how far should we put it away, and that is the distance that we're looking for. So we should put it radical 5 feet away from the painting in order to maximize beta. If you wanted to figure out what beta was, you could go ahead and punch that into your calculator, and you would get beta equal to approximately 0.7297 radians, which if you wanted you could convert that to degrees at that point, divide by pi and multiply by 180. That's approximately 41.8 degrees.